Welcome to space. So you might be wondering what I'm doing in space. Well, I'm here to do an experiment and I would like you to join me in this. So for this, I've got a glass box which is specially insulated and in it I've put billions of rubidium 87 gas atoms. And now I have put some lasers around it which will cool them by taking away all the excited atoms from the rubidium atoms. You can also think of it as sweat evaporating from a skin. Start to cool these atoms till critical temperature, which is minus 243 degrees Celsius. And what we observe is very interesting. All the atoms get slower and slower and come closer to each other, and at minus 243 degrees Celsius, they club together to form a single superatom. Single superatom is what we call the Bose Einstein Condensate. So I know many of the questions have been arised in your mind, like what is a Bose Einstein Condensate actually, and where do we use it, and why I have used these rubidium atoms, and also why I have done this experiment in space. Well, I will answer each of your questions, but first of all I want to go back to Earth. So first of all, we must understand that the first four states of the matter have properties which could be understood at the atomic level. But the fifth state of matter is not so simple. It has properties which could be only understood at a subatomic level. At the subatomic level, there are two fundamental particles which are the bosons and the fermions. They are further divided into different categories. So you might be thinking, what is a fermion and what is a boson actually? And where do we get the idea for the fifth state of the matter? Well, for that we have to take a look at the properties of it. The first property of the bosons is that they follow the Bose-Einstein statistics, or simply meaning that they are indistinguishable or non-separable. Secondly, they have integral value of quantum spin numbers, which means that they will take a spin of 360 degrees to come back to the original configuration. The third property is that they have symmetric graphs of wavelength functions, and which in turn means that they will not follow the Pauli's exclusion principle. And what will it lead to? It will lead to the fact that they can lie as many as the bosons in the same quantum state. Well, this is not the case with the fermions. The fermions have completely different properties. The idea for the fifth state of the matter comes from the fifth property of the bosons. Let me show you how. Here we have the atoms of a Bose gas, and on cooling them, they come into the same quantum state or the ground state, and together they form a condensate. This phenomena is not possible on Earth because the gravity will play a role and interact with the Bose gas atoms and will not allow them to form a condensate. So we have studied all about the fifth state of the matter, but what are its uses? Well, it could be used to prepare superfluids, as also superconductors, which could be used in the quantum computing. And also, many scientists believe that this can also help us explore the dark matter.